very happy to have Tim Caswell with us today, who is a very distinct expert on Node.js. You'll see about 100 GitHub projects for him, ranging from database drivers to binary format codecs. He is part of the Connect Web framework that is behind Express.js. He does control libraries, template engines, and more. So without further ado, here's Tim Caswell.
Thanks.
He hasn't realized I'm a little stubborn. Okay, that's it. I give up.
Try a little more. All right. So, quick show of hands. I don't know this audience very well. How many of you have used Node.js? All right. How many of you have never used it but want to? Who's not even heard of it? Wow, I guess we've done a good job promoting it. So, wait, keyboard should work. So about me, my handle online is Creationix. You can find me on GitHub, on Twitter, pretty much anything by that. I like to create things using Unix, and so I'm Creationix. And I'm a longtime Node.js contributor. I've been part of the project since long before it was even popular, since early 2009. I created a blog called howtonode.org because I was tired of answering the same questions over and over on the IRC forum. I've spoken at over a dozen JavaScript conferences as far as Shanghai, China. And I have over 100 open source projects on GitHub, way more than I can possibly maintain. I love programming, I love teaching programming, and I love new tech. So here I am teaching about new tech. And I don't know how many of you are locals, but I'm from a small town in Texas, and I'm always trying to bring tech to my town. So I'm glad that we have a conference here bringing tech to this town. I think that's awesome. So, what is Node.js? On the website, it says Node.js is a platform built on Chrome. You've read that before. But it's a whole lot of marketing speak saying it makes fast servers, right? Well, what I say, Node is the scripting interface to your operating system. It lets you do anything your computer can do, but with a nice JavaScript evented interface. You want to make your computer do something? Use Node. You can probably do it. It's especially useful for anything that involves input-output. Well, what else is a computer going to do? I mean, I guess you could like generate bitcoins or calculate Fibonacci numbers, but for the most part, you're interacting with other systems. And Node is basically a fast JavaScript engine and an efficient event loop library. So this is a slide from Ryan's first talk in Berlin in 2009. This is performance of Nginx versus Apache. On the horizontal scale, we have the number of concurrent connections, and the vertical scale is requests per second. The yellow one is Nginx, and as you see, it handles the concurrency pretty well, whereas Apache starts to fall apart. And the difference is Apache is spawning a thread per connection, whereas Nginx is using a single thread, is using an event loop. So event loops perform well under concurrency. What about memory? Well, so that bottom one there is Nginx, pretty much flatlined. It's just a small struct data structure to hold the pointer to the socket per connection, whereas you need an entire operating system thread per connection on Apache. Those aren't cheap. Or if you're using a multi-process module, it's even worse. So the idea that event loops scale is not new. This idea has been around long before Node. So what is different about Node? And just to make sure that we're clear on what I/O needs to be non-blocking, what are the relative latencies of getting data? So these numbers are a little old. This was on a computer from a few years ago. Grabbing something from L1 cache and Intel CPU is about 3 cycles. L2 cache is about 14 cycles. RAM is 250 cycles. That's pretty fast. Getting it from the hard drive, well, you got to seek the drive, and you got to read it, and then you got to go through the bus, and maybe it's SCSI or ID or whatever the hard drive uses. I mean, there's a lot of machinery involved. 41 million cycles. And if you're going across the internet getting something from Europe, that can be 240 million cycles. That is a big jump. But that's less than a second. That's a fraction of a second in our time. And so as users of computers and as programmers, we often don't see this big jump. We don't realize it is that much worse to get something from the disk than get something from RAM. So I'm going to put these in human terms. Let's pretend that one cycle is 1 second, because we can do about 1 addition per second in our head if we were computers. So L1 cache is grabbing a piece of paper from your desk. L2 cache is getting a book from across the room. L3 cache is going across the office. Or we could roam the earth for 16 months to get something from the disk. Or go on a 7-year journey. Which of these are you willing to have your work waiting on that data? And which of these is it worth the overhead to save your work and work on something else for a while? It's pretty clear where the line is. Some of us might even say, well, at the RAM level, but it's a lot of work to get all that set up and saved. There's definitely a line here. And so when I say non-blocking I/O, what I mean is your process never waits on getting things from the disk, getting things from the network, because you waste so many CPU cycles. Now, in modern computers, they don't actually sit there and wait. They suspend your thread and let other operating system threads do their thing. But in order to handle concurrency, you now need a thread for every user, which, as we saw in the other graphs, doesn't scale well either. So just in case this wasn't abundantly clear, I have a human analogy. You go to the doctor, and there's a waiting room, there's a sign-up, there's a window. Maybe you're just going for a dental checkup or a health checkup, and she hands you a form, right? And says, fill this out and sit down. And if it's your first visit, maybe there's 20 papers in that form, if you're lucky. Could be more. Now, here's what you're going to do. You're going to stand in the window and block the window while you fill out all 20 forms, right? No. You're going to sit down so the next person behind you can go talk to the receptionist and fill out a form in the chair. Which is cheaper, building 10 receptionist windows or putting 10 chairs in the room? It's common sense. The only reason we don't do this with computers is because it's a fraction of a second to do the 7-year journey. So non-blocking is obviously more efficient. There are downsides too, but in the case of network servers, I think it far outweighs the downsides. So if you've done much Node before, you've seen this kind of JavaScript. This is a basic TCP server. Node is the server. You don't put Node in Apache. You don't put Node in a Java whatever container. Node is the server. And so you just write this, what's that, 6 lines of code plus comments. And I have a fully working TCP echo server that's non-blocking. It's a web scale echo server. This could probably handle 200,000 concurrent clients that says whatever they say back to them. Isn't that what Reddit does? So here's an HTTP server. So you want a web browser to talk to it. Node has a built-in HTTP library that handles the HTTP protocol for you. And so you can just create a server, and every time someone connects, this function will get called. And you can do whatever. And in this simple case, we're just going to send some HTTP headers back and say hello. And this is actually a very high-performing web server. Each connection uses a fraction of RAM. And on this MacBook Air, it could probably handle 20,000 requests per second on one CPU core. Pretty good. Pretty good for a language that used to be considered a toy language 10 years ago. And Node has all sorts of nice primitives. There's a child process API, where if you need to do something that's not built into Node, you can just shell it to the operating system, and you get a full 3-way non-blocking stream. You get standard in, standard out, standard error. You can read them, you can write to them. And again, it's non-blocking. You get buffered file I/O, which is nice because when you actually do C code and low-level stuff, there are no asynchronous file APIs. Not reliable ones, at least, and nothing cross-platform. And so what Node actually does is internally there is a thread pool for file I/O, but at the JavaScript layer, there is only one thread. And so you don't have to worry about locking or mutexes or any of that, but you still get the benefits of never waiting on the disk I/O. And it's a pretty efficient thread pool. So this is actually an API that I added to Node about 3 years ago. Before this, to read a file, you had to open the file, give it a callback, that gets your file descriptor. Then you got to read the file at an offset, give it a callback. It'll tell you how many bytes it read. And you got to recursively do this loop until you get all your data. And then you got to call close and give it a callback, and 40 lines later, you write a file. And I said, you know, that's a pretty common use case, Ryan. How about we just write a file where they give it the file name and you give them the data? And so he's like, yeah, pull request. So I wrote the code, and it's since been written 10 times, but I did initially write this. Read file is handy. Or if you want to do streaming data, if you don't want to buffer all the data, Node has file streams that are very easy to use, and you can just pipe them to other things. Anything that's a stream in Node can be piped to another stream, just like in Unix where you use the pipe symbol. And this was something that we had meetings about in some upstairs Oakland office many years ago, and it turned out to be a good idea. People love streams and piping. You also get events on streams. So if you don't want to use pipe, you can get the actual events. And there's timers, which aren't really I/O, but they are still event-based. If you want to say, when 5 minutes have passed, do this thing. You don't want your process just sitting there twiddling its thumb for 5 minutes. You want to do other stuff. So again, it's a non-blocking API. And we even have readline prompt, which is handy if you want to like old school learn to program examples where you say, what is your name, get the result from the user, and then put it back. You can't say result equals get line, because then you'd be blocking on user input. So anything that involves I/O or user input or time has to be non-blocking to keep the system fast. And that's the downside of this model. But like I said, it's well worth it, because then your process is never waiting on things that take ages in computer time. So when you're working with Node, there are some basic general concepts that are really good to understand. And these aren't in any particular order. The first one I'm going to go over is single-purpose modules. In the Node ecosystem, libraries tend to do one thing and do it well. A lot of the people who started Node believe in the Unix philosophy. And what this ends up looking like in a JavaScript API is you just have one file with one export that's usually a function that takes some options. And for example, this is a logging middleware for a new system that I'm working on currently. I wrote the Connect system that Express uses a few years ago, and this is a new one I'm working on. It's similar. So the entire file is one module export, which is a function. So if you require this file, what it's going to give you back is not an object, but just a function. And you pass in an app, which is the layer beneath you, and it returns a function, which is a new app. So this is a very functional-based API. And then basically what this does is it takes your app, which in this web system, an app is just a function with a certain signature, returns a new app. Basically, it's mutating your app using a very functional style of programming, and it logs all the requests. The specifics don't matter, but the important style is it's a simple function with one export. And whenever possible, we do that in Node because it keeps the code nice, modular, and decoupled, and often leads to much simpler systems. And I'm sure many of you have worked on the 500,000 or million line code bases and realize that simple is good. If you can get away with it, simple is good. Sometimes you can't, but if you can. And here's using that function. So I'm going to create my app, which is just a function. I'm not using any library or anything. It's just an interface, just a convention. And then I require the log function, and just call it, pass in my app, I have a new app. It's a loosely typed language, you can do that. I could even turn a function into a string, but it's generally good to stick to the same type. So the next thing that's very important is understanding async functions. This is not the right order. Oh well, we'll see what happens. So in a blocking system, you have function calls where there's a call stack. Everybody understands a call stack. I assume there's lots of programmers in here. But let's review. You have a call stack. You call a function. Your state's put on the stack. You're in this new function. And eventually, it's going to return a value, and the stack's going to unwind. Or if your language has exceptions, it can throw an exception, and then it unwinds until it finds an exception handler. But either way, your stack builds, unwinds, builds, unwinds. JavaScript is no different. But you can't do that with non-blocking code. So what you do is you call your function, pass in a callback, which is an anonymous function, which is a value. Unlike in most stricter languages in JavaScript, functions are just values. Your stack immediately unwinds, but you still want the behavior of this function that either returns a value or throws an error. But you can't use return or throw because your stack's already unwound. Both of those depend on the stack. So what Node has is there's a convention that the last argument is always a function, and the first argument of that function is always the error. So if there was an error, if an exception would have been thrown, you instead pass that as the first argument to the callback. And if you would have returned a value, you pass that as the other arguments to the callback. So you get the parallel, but it's non-blocking. So back to the read file example. We read the file, we pass in some arguments, and then the last argument is my callback, which I just inline an anonymous function here, indent the code, and I can keep on going. But the way this actually executes is fsReadFile will call, increment the stack. It will then immediately return as soon as it registers this callback at some system level somewhere and execute this next line. And so this next line will actually be called before that callback ever happens. So you got to be aware of that. It's still run to completion. It's still single-threaded, a single call stack. And basically, you have a bunch of really tiny stacks where you do some things, set up events, unwind, you're done. And then eventually, one of those callbacks will get triggered by the system because data happened on a socket, or the disk finished seeking, or something external. A new stack happens and unwinds immediately. And this can lead to some hairy code. So one very useful function is wrapping async code into larger composite functions. So maybe I want to read this and do that, and I can't show complicated code on one slide, so here's a simple example. What's this do? This reads a file and capitalizes the result. Very useful, I'm sure. Maybe if we're making a Reddit bot or some social media, I don't know. Why am I picking on Reddit today? I don't even use that. So here I'm calling the built-in read file from Node. When I get the result, if there was an error, I have to forward it to my callback. This is very important because remember, try-catch doesn't work because the stacks are always short. So if you don't forward your errors explicitly, your errors don't get routed, and that is bad. And then there wasn't an error, so I passed null for the error and then transform the results, and there you go. I just made a custom read file that uppercases everything. If I want to do two things at once, then I have to wait till the first one's done before I start the next one because my code's not blocked anymore. So I'm going to get a file name by some username. I'm going to assume this is a database lookup of some sort. I'm going to pass in onGetFileName, which is a reference to this function right here. One really nice thing about JavaScript function statements is their value is hoisted the entire scope. So unlike in C, where you have to have a header file declaring the function before you call it, in Java, if you use this syntax, you can call that function anywhere in the block. So you can write your code in the order you want it to happen and just keep passing these references as your callbacks. So getFileName is going to execute, the function will end, your getUserFile will return, and then later on a later stack, onGetFileName will get called. It will then call readFile, which will return and be gone. And then later in another stack, onReadFile will get called. So it looks ordered. It looks nice. In the simple case, however, you don't need to do that. You can just nest it. Nesting is not evil. It's just evil in excess. If you've only got 2 levels of indentation, just nest. It's simple. I do it all the time. Closures of nesting are awesome. If you have the Great Pyramids of Egypt, you probably nested too much. I have seen code where it's like 60 characters in, 60 characters out. And this is also why most Node people use 2 space indents instead of 4, because you indent all the time. Doing things in parallel is a little harder, but it's also something you can't even do in a blocking system. In a blocking system, you can't say, go read from the database and read this file, because it's read from the database, wait, read from the file, wait. And Node is possible, but it's complicated. This is actually very bug-ridden code. If anyone can see the 2 bugs, that would be great. I know what they are. But basically what it does, it takes a page ID and author ID, does this mythical database lookup, and does this other mythical database lookup. And we don't know which one will return first. It's completely indeterminate. And so what I do is I store the results in these variables in the outer closure, and then check if the variable is set. Has anybody seen the two base conditions yet? That's a typo, yes. Thank you. I didn't see that one. Yes, that should be if page, you're correct. The two race conditions are, one, what if both of these emit errors? Then whichever one happens first is going to return callback with error. And then later, in some later tick, the other one is going to have an error, and I'm going to call callback again with error. And that is a big no-no. If you run an async function, never call the callback twice. Because the code that's calling you is not expecting that callback to be called twice, and all sorts of mayhem will ensue. So I actually need some other sort of variable or counter that says, did I return yet? And I need to check that before returning. So writing this kind of code can get tricky, and there are abstractions for solving this. There's the promise abstraction, which solves all this with a library. And there's other patterns. There's control flow libraries like I wrote one called step. There's a very popular one called async. And there are problems. The other problem is less minor, but since this is dynamically typed language, what if one of the results was a falsy value? Like what if null was the right value? And here I'm using if author to check if it had returned it. So I need yet another flag to say was there a return value even though it was falsy. But I couldn't fit that much code on one slide, so I left the bugs. Event emitters. So all of that was about async functions, which is the unblocking representation of a function call. Now there's also the event emitters. Since it's an evented system, these are very common. And basically, I think event emitters happen anytime you have external inputs, usually human inputs, or a stream of data. So if you've done browser JavaScript, which I'm sure a lot of you have on click, on page load, on key down, on key up. These are all events. These are all things that happen when the user of the browser does something. Well, this happens in the server all the time too. On file open, on file, no, those are more async. So event emitters would be like you have an HTTP server and on request, someone hits your web server. This isn't something that happens once and only once like an async function. You can have 0 hits to your web server, it'll be a very sad day, or good if you're an ops. Or you can have 1,000,000, which is inverse. It's any number. And these event handlers don't have the error property. There's instead a separate error event type. And in Node, if you don't have a listener for the error event type, and an object emits an error event, it will throw an exception, which will crash your server. And that's our way of saying, you should listen for this error event. Because nobody wants their server crashed. Because remember, this is single-threaded. This thing can handle easily 200,000 concurrent customers. And isn't it great when 200,000 customers suddenly get disconnected? Check for errors. So here's an example using that readline library. So there's a line event. Whenever the user enters a line of text and hits enter, there's a close event when they close it, and there's a whole lot of other events in the docs. But as you see, the way this works is you say object.on. You can also say attach listener if you want the verbose syntax, but we like on much better. The event name, and then the handler with whatever data. Very simple API. Creating your own event emitter is easy. You just load the event emitter class, create a new instance of it, and then you can listen for events and you can emit events. Now the actual emitting of events is synchronous. So when I say emit speak, all the event emitters for speak, however many there are, will get executed before that event returns. So be aware of that. It's never a problem usually, but a lot of people think, well, if I'm using events, then it's asynchronous. No, it's not. It's single-threaded. There's nothing to wait for. It's not an external system input. It's just me and the code saying emit this event. So that is fully synchronous. If you want to use your own constructors as classes, you can inherit from event emitter. Here I'm using what do they call it in TC39? Wonderbar proto? I think that's what they call it, with the double underscores. Dunder, that's what they call it. Dunderbar. So in Node, there is one JavaScript engine, it's V8. So not only do you know exactly what version of JavaScript you're running, but you can even use non-standard things like proto. I mean, people will yell at you and say you're doing it wrong, but it works and it's efficient. And this is how we make a class inherit from another class. Node also has a util.inherits function built in if you don't like this. There are many ways to do inheritance. And here in my constructor, I'm calling to the super constructor, and even that isn't really required. Although in the newer nodes, since Node 08, I think that makes the domains work better. I think they put some hook, because it used to be before that, the event emitter constructor was empty. And it's very easy to make any custom class that's also an event emitter. All right, so streams. Streams started out as a special kind of event emitter that always had the same type of events. So a stream is, suppose you have a web server and you're taking a file upload or a form upload, anything with post data. Node's not going to buffer that entire thing for you because they could be uploading a 2 gigabyte video file. In fact, there is a Node-based startup in Germany called Transloaded that what they do is they upload multi-gigabyte files and transcode them for you. You definitely don't want to buffer that to RAM on your server. Or reading from the disk. There's a lot of places where you want to stream the data. It's much more efficient. And usually it's just raw data, just raw bytes. Sometimes people will stream objects or documents, but for the most part it's bytes. And so Node standardized the stream API, like I showed earlier with the piping. And that should have been more slides. Okay. And then really just understanding JavaScript. A lot of people think they know JavaScript because they did browser. I mean, I did browser JavaScript for 10 years before I started Node. I had my own startups. I thought I was good at JavaScript. And then, like, I did not believe Malte when he told me that, well, you can't use try-catch with non-locking functions. I'm like, sure you can. It'll work. It's wrapped around it. It'll catch it. But no, he was right. The stack of lines, the try-catch will not work. I thought I knew JavaScript. It turns out when you're using this kind of non-blocking code, you really need a deep understanding of the language. So I wrote this series on a blog post on how to Node called Object Graphs, and I'm just doing a few highlights here. Seeing how the engine works, how the language works as graphs, help me understand it. So here's a simple one. I'm creating 4 local variables, giving them values. And in my graphs, if they point to the same value, I'm going to point them to the same thing. Implementation-wise, it probably doesn't point to true. It probably is just an inline box value. But yeah, that's it. You have your top scope with 4 keys. Scope is an object. Scope in JavaScript is an object. That's important. Everything in JavaScript is objects and references. That's it. Well, functions are special objects. They're just objects and references. There are no classes. There are no static binding. There's none of that. If you... What did I do here? That's misleading. All right. Well, this is prototypal inheritance, contrary to what the title says. So this is just an object literal. This blue one here, which has name, age, as programmer likes JavaScript. And then I use object create to create a new object that inherits from that. And I set a couple of properties on that. And those are both referenced from the local scope, which is another object. And so in my code, if I were to say jack.age, it would say, where's Jack? All right, that's this object. All right, .age, where's age? Okay, and the value 4. And then if I were to say jack.likes JavaScript, then it would do that. It's not there. It would defer up the inheritance, find it there, and you know, that's basically how it works. This is why the original JavaScript implementations were interpreters. Implementing this with an interpreter is very easy. You just have data structures in memory and just walk them. It's very slow. People at Google and Mozilla and Microsoft and the various engines have done amazing things taking this semantic and making it fast. JavaScript code is often faster than C++ code if you write it right. And that's just amazing. This is the slide I was looking for. This is where I forget my var statement. And instead of creating a new variable in my local scope, it goes to the global scope, which the local scope inherits from, which will pollute things. Closures are objects too, did you know that? I didn't, until I was writing the blog post. So this is a very, very simple closure function. It takes name and returns a function, which closes over name, which then returns name. It's like, tell me what my name is later when I forgot. And so description 1 is a function created by make closure, close the closure. Description 2 is another function created by that one, Albert the Awesome. So whenever I call description1, it's going to return closure. And 2 is going to return L or the awesome. But how does that work? How is that stored? They're just objects and spaghetti references, right? Yep. So like I said, functions are just objects. But they have this scope that they were defined in. Every time you create an object, every time you create a function in JavaScript, that is a runtime event. You are creating the function. It's not a static thing at compile time like a static languages. You are creating an object with this lexical scope. And it records that in its object with a pointer to that object. You can't get it from the language, but it's there. So when I called make closure, that returned me an object, which I then stored in description1 in my local scope. That has in its scope what was inside the function, which is the parameter name, which is another object. So every time you call a function, a new object is created for the scope of that one time the function was called. And since I returned a function, that function has a scope. It's kind of like inheritance, but it's for local variables and functions. And so really, is this any different than an object with a name property? Not really. Except now you don't have to worry about this because it's lexically bound. Any of you have gotten bit by this changing on you in JavaScript? I certainly have. And so really, it's the same. Closures are objects. They're just used differently. Understanding this is very important because in an event-based system like JavaScript, you're going to use callbacks everywhere. And if you try to use normal, traditional class-based programming, you're going to have to bind all your event handlers statically using bind or manual closure or something. Because if you don't, when that event happens on the new stack with the new scope and the new everything, it's going to be in the wrong context. And when you say this .name, it's going to be global.name, and you're going to just crash the system. So here is an example showing that functions are not statically bound at all. A lot of people coming from Java are confused by this. So I'm going to create this object literal. It has two properties, name and description. Name is just a string, description is just a function, return this .name. So at first glance, it looks like that function belongs to lane. You would think that's lane.description. And if you do lane.description, you're right, it'll return lane lambda. It'll work. So let's also make another reference to that function as a local variable description. I mean, they're just references, right? Let's make another. And then let's make an object Fred, which has the same lane.description as its description. I mean, we don't have to inherit. We can just manually copy functions around. It's a loosely structured language, why not? But it has a different name. Now, what happens when you call these? So if you call lane.description, that's going to return lane lambda. When you do Fred.description, that is not going to return lane lambda, because this is now Fred the functor, or the object that has Fred the functor's name. If I call description, it's the same function, right? That's going to probably return undefined. Depends, because it's now being called in the scope of window or global or whatever is the default. Or if you're in strict mode, it's going to throw an exception because it's then null. Or I can just call it directly with my own custom object because all functions in JavaScript have call and apply methods that say call it in this scope. This, that was repetitive. So it's going to be z to z. What does that look like in a graph? Well, it looks like this. There's only one function in memory, the same function. It's referenced by Fred's description, it's referenced by Lane's description, it's referenced by the local variable description. And as you see in this graph, it's not owned by any of those. It's just a value they all three reference. And so if I have some API that needs a callback, I can't say Fred.description as my callback, because what it's going to see is just that orange function without any reference of where it came from. And so when it calls that orange function, it has no idea that you got it from the Fred function or the Lane function. This is why you have to bind things. Whereas with the closure factories I was doing before, it's all lexical and it's always bound where you want it. So both methods are very useful. This method is very efficient because you're reusing the same function everywhere. You just got to be careful about what scope you call it in. The closure method is safe and simple because it always has lexical scopes. Let's see. Here's a classical constructor. This is the closest thing to a class you can get in JavaScript. You create your constructor as this, you have your prototype with your methods, do things. This is a rectangle with area and perimeter. This is a square that inherits from the rectangle. We're going to optimize perimeter to be width times 4 because we know they're all the same. You probably see this kind of code in every intro to object-oriented programming course out there. You can do this in JavaScript. Just be aware that those aren't really methods. They're just functions on some prototype. Now, how does this work? So, we can dynamically add another method to rectangle, and Square will inherit that. It's a nice two-string method that shows me the area and the perimeter. And then I'm going to create a rectangle, I'm going to create a square, I'm going to log the dumpable for this. Here's what that object graph looks like. So where's the constructor? The orange on the top right, that's my rectangle constructor. And that blue blob next to it, that's rectangle's prototype. So a class in JavaScript is really just this function prototype combo, this pair. That's the closest thing to a class. And then an instance of rectangle is this blue object that points to rectangle's prototype. And then when I made square inherit from rectangle, what I really did was I made square's prototype inherit from rectangle's prototype. So now when I make an instance of square, so if I have square here, and I'm going to do square dot toString, it's going to be square, toString, not there, there it is, all right, that function. So I'm going to do that orange function on the far right in the scope of this blue square on the far left. And it's going to look for this dot width, this dot height, this dot constructor name, and this dot constructor name. And then the graph just walks back and forth to execute your code. Modern engines make this fast, but it's a lot of work. None of this is statically bound. It's all dynamic, which is good and not so good, depending on how well you understand it. Sometimes I like to use pure prototypal. And here it's just an object. I'm not using a constructor. I put a name on it. It's got some functions. I want to make another object that inherits from that object. So in ES5, you have object create. I'm going to just override some properties, and this is basically my subclass, but really it's just a new object that overrides some properties. To create an instance is the same way. I just create an object that inherits from that object because it's a prototype, it's not a class. Everything's an object. Override some properties, and there you go. I tried to make the style of programming popular, but the engines don't optimize it very well. It's quite a bit slower, and by quite a bit slower, I mean, well, darn, you can only do this 30,000 times a second instead of 500,000. Unless you're going to be doing a tight loop, it doesn't matter. But people still get up in arms and say you're evil if you do this. It's very interesting. But it's still good to understand you could. And this graph is slightly simpler. We don't have constructor functions. We just have prototype objects with methods, which are really just function properties. And then objects that inherit from them, those are the instances. And then one more, if I haven't made your brains explode with graphs yet. Is this too much? It's the last one, I promise. This is a model view controller thing I just made up. I try to make it as simple as possible for the graph. So this is a closure factor. So you pass in the model and the view, which implements some interface that's defined elsewhere, hopefully in your docs. I'm going to hook the model and the view together by calling some method on the view. I'm then going to return this new object, which has these functions. And here I'm not using this or anything because I can reference model and view from the closure because it's flexibly scoped. And so basically, every time I call controller, it's going to create a new object with all this nice stuff. And then here's how I would use it. So I'm going to create a controller. I'm going to call it on. Probably not the best name for a controller, but whatever. And I'm just going to make a mock model and a mock view with some made-up interface that I made for this presentation. And there's the update function where it ties them together, the close and save and value. And then I'm going to asynchronously up, on down, on save, and these callbacks. And since this is closure-based, I don't have to bind those. There's no this to worry about. I can just pass the methods directly to the event handlers, and it'll be called in the right scope, which is really nice. And here's what the output is. View now has 5, view now has 6, view now has 5, saving value, now you can view it. It all works. Makes total sense, right? Here's the graph. Hopefully that's legible. So there's my factory, the function on the top. It's not actually hooked to anything. It returns this object on, which has three different functions, all which share the same scope because they were created in the same scope. And that was the scope of when controller was being executed. And within that scope, I have the two objects that were passed in as view and model. And then those, of course, have their properties that I gave them explicitly. And so here I returned an object that has a whole bunch of functions that all share the same scope. Now, if I were to call this 10 times, I would have 10 copies of those 3 functions. But each of them would have their own unique scope. So depending on what you're doing, this could be more efficient or it could be less efficient. If you're going to have to bind them and have to an event emitter anyway, what bind does is basically takes your shared function, creates a copy of it, and binds it to a scope. So why not just do it explicitly from the get-go? I think it's actually more efficient if you're going to be using event-based code. And that is my time. I will this afternoon. Oh, this is my laptop. That's my So, do I have time for questions or am I done?
You have time for questions.
All right, we have any questions? I can't see very well.
All right, Tim, I'm coming up.
Coming up?
Any questions?
Any questions?
Going once?
Cloud9 was written in Node.js, and that's a popular online. Could you talk at all about that in terms of whether you like the way that they put that together or ways that it could be improved?
So I worked at Cloud9 for a year. And we wrote a lot of their backend. It's a fairly complex server, probably the biggest node code I've ever seen. The actual app itself is a great idea. The only problem I have with it is it doesn't work offline. And I'm always traveling. I need something that works when I'm online. And so actually a project I'm working on next month, if my Kickstarter gets funded, there's a way to do development offline in a browser, where you can do real development on a Chromebook offline. I think I can make it work. We shall see. It involves implementing Git in JavaScript and using a fake file system in the browser. But if it works, it'll be great. Otherwise, Cloud9 was great. It's just when you're not connected or you have latency, it's a problem. But as far as the technology, the browser was fast. And the editor in the browser was amazing. I like it better than Sublime TextMate.